Okay, thanks, Tristan. I guess I should thank my fellow co-organizers for allowing me to volunteer to fill in on a last-minute cancellation. So I only realized I was going to give this talk 2 days ago. This is a talk I gave in at UBC in October. So I did manage to change this and add the archive number. I haven't changed anything else. And so it's joint work with Shubham Dwivedi and Karigiannis that went on the archive about a month ago. And I also apologize to Tristan and Bob and all the other flows experts in the audience. The first 5 or 6 slides are not for you, for people who are not flows experts. But then eventually I will get to flows of G2 structures and tell you about sort of one of the main results in this paper. And feel free to interrupt me whenever you can. So as I said, I'm going to start off very basic. What is a geometric flow? If we have a manifold and some geometric object U associated with M, we can ask for the best, in quotation marks, such object. So for example, we're looking at metrics. Best could mean, depending on who you ask, could mean Ricci flat. If you have an immersion into some existing Riemannian manifold, then best immersion could mean minimal. And the notion of best is usually described by this object satisfying some geometric nonlinear PDE, which is often elliptic. And I'm just going to write it schematically of this form, P of U equals 0. So P is some nonlinear, usually elliptic differential operator. So suppose we start with some object that's not the best, doesn't satisfy our best condition. We can try to evolve it in time in some geometric way to improve it, right? To make it be closer to being best. So that's a geometric flow. So U as a function of T is evolving in time by this operator P of U of T. So it would stop when P of U of T is 0, right? And we have some initial condition. So for example, the Ricci flow, the mean curvature flow, and I don't need to tell anyone in this room probably anything more about that. So what kind of questions can you ask if you're looking at a geometric flow? So one of the most fundamental questions you can ask, the first question you can ask is, well, does this even make sense? If I write down this PDE, then do I know that there's a solution, and hopefully a unique solution, at least for some small time, right? Does there exist some epsilon positive and a unique smooth solution on some time interval? If these flows were strictly parabolic PDEs, then there's this sort of general machine of short-time existence and uniqueness for parabolic PDEs, but often they're not because of diffeomorphism invariance. And there's a sort of well-established procedure now called the de Turk trick, which sort of breaks this diffeomorphism invariance. It's a gauge fixing. And you use that to sort of establish short-time existence and uniqueness. Essentially, what you do is you show, well, this flow is not parabolic, but it's in some sense equivalent to this other flow, which is parabolic, in the sense that you can show there's a one-to-one correspondence between solutions to these two equations. And for the parabolic equation, you can hit it with this machine and get short-time existence and uniqueness. If you have that, then of course you can ask, does it exist for a long time? Can we take this epsilon to be infinity? Usually we cannot, right? Geometric flows develop singularities in finite time, and something bad usually happens at the singular time. Some scalar quantity, some norm of some tensor is blowing up as t goes to tau. And then even if it does have long-time existence, it doesn't mean it needs to converge to anything, right? So the limit, even if U of t makes sense for all t up to infinity, doesn't have to have a limit. Another thing you can ask is, does this flow have stability? If we know that our initial condition U naught is not the best, but we know for some reason that there is a best one close to it, then often you can show that your flow will exist for all time and converge to a fixed point of the flow, a best one. But it doesn't have to be the one that you know was close enough, right? It might converge to something which is diffeomorphic to the best one that was close enough. Okay, so now that's sort of the introduction for those of you who aren't experts about flows. Let me talk about a particular geometric structure, which is a G2 structure on 7-dimensional manifold. And I know there's a few people in the audience who know quite a bit about this, but not everyone, hopefully. So this is the kind of geometric object I want to study, and I want to flow this to get sort of a best one, whatever that means. So here's the definition that's good enough for us. If we have a smooth 7-dimensional manifold, then a G2 structure on M, if you're a topologist, it's a reduction of the structure group of the frame bundle from GL7 to G2. You can think of this exceptional Lie group G2 as a subgroup of GL7, and in fact, it's a subgroup of SO7. So if you have such a reduction of structure group, you also have an orientation and a metric. And for a differential geometer, really all you need to take from this is that you can encode this reduction of the structure group in the existence of a special kind of 3 form on this 7 manifold, which is non-degenerate in a very strong sense. So if you know what a multisymplectic form is, it is, you know, if it was closed, it would be a multisymplectic form, but it's more non-degenerate than that. And it's a fact that not all 7 manifolds have these reductions, but lots of them do. So the topological characterization of when a 7 manifold admits such a G2 structure is if and only if the first 2 Stiefel-Whitney classes vanish, so orientable and spinnable. And then if you have one, you have lots of them, because the set of these positive 3 forms, non-degenerate 3 forms, is open. So if you have one, you push it a little bit, it's still going to be non-degenerate. And as I said before, G2 is an SO7. So when you have one of these, you get for free a metric and an orientation, but you get it in a very nonlinear way. So the map from the 3 form to the metric is very nonlinear. This is how you can see it. The left-hand side here only has phi in it. And this expression is symmetric in these 2 vector fields x and y, and it's a 7 form. It's a top form. So this constant is not so important. It's some constant times g of xy times the volume form. So from phi, you can determine g times the volume form. And then because you know it's a 7 manifold, you can extract separately the metric g and the volume form.
How does the volume form associated to phi? So we can be phi.
So from this expression, you get, if you write it in local coordinates, this is gij times square root of determinant of gij, right? And then you take the determinant of that, and so that expression is some cubic expression in phi. So once you've extracted what g is, well, actually you can extract it root of determinant g, and then you get g.
But then it's also showing you direct formula. Okay, fine.
There's not well, there's a direct formula. So the volume form up to a universal constant is phi wedge star phi.
Okay.
But you can't get star until you have the metric.
Oh,
so
yeah,
it doesn't make it any easier. Okay, so suppose we have
But the volume form association phi is also the volume form association G.
yes, yes. G phi it's the volume form of G phi. That's right. Everything depends on phi. Okay, so we have a metric, we have an orientation, we have a Hodge star. I'm going to call that star phi just to remind us that everything depends on phi. And therefore the 4 form, the Hodge dual 4 form, which we call psi, is the star phi. And the metric, of course, determines a Levi-Civita connection, which, again, if I'm being careful, this will be nabla of phi, right? Because it depends on phi. So what is the torsion of a G2 structure? It's the obstruction to phi being parallel with respect to the Levi-Civita connection of the metric that it induces. So this looks like a linear equation, but it's not, because nabla depends on G, which depends on phi in a nonlinear way. It's a nonlinear PD. And you can actually show that it's actually easier to package this data in the form of a 2 tensor T, which we'll also call the torsion. Essentially, nabla phi is a contraction of T with the 4 form, and vice versa. You can get T by contracting nabla phi with the 4 form like this. So T vanishes if and only if nabla phi vanishes. It's just easier to work with a 2 tensor than this tensor here. And we say that the manifold is torsion-free G2 manifold, and in older papers, you'll just see it say G2 manifold if it's torsion-free. Okay, so this, as I said, this is a fully nonlinear first-order PD for this unknown positive 3 form. So something that's not obvious was proved by Fernandez-Gray in the early 80s that being torsion-free is equivalent to being closed and co-closed. So of course, any parallel form is always closed and co-closed, but the converse here is true, right? So if it's closed and co-closed, then it's necessarily parallel, and you don't need any assumptions of compactness here. This is just a representation theory proof. Okay, so we're going to use this fact because what we really want to achieve is torsion-free G2 structures, and the fact that we can equivalently describe this by being closed and co-closed makes it a little bit easier to deal with. Okay, why should we care about torsion-free G2 manifold? So if we had one of these, torsion-free G2 manifold, then none of this is, well, this part of it's obvious. The metric is Ricci flat. That's a calculation. It's not immediately obvious. The holonomy lies in G2. That is obvious if you know that the group, the subgroup of GL7 that preserves this 3 form at any point is G2. That's another way to define the group G2. And then by the general holonomy principle, the holonomy of the Riemannian metric will be contained in the group that preserves all parallel tensors. Okay. These spaces are important in physics. Let's not talk about any physics today. But they basically play the role in 11-dimensional M theory that Calabi-Yau threefolds play in 10-dimensional string theory. And we're going to say that a torsion-free G2 manifold is irreducible if this holonomy is exactly equal to G2, not just a proper subgroup. And this is what we really care about, because if the holonomy is contained in G2 but is strictly smaller, then it's something we understand a little bit better. Up to a finite cover, it's going to be a product of a circle and a Calabi-Yau threefold, or a 3 torus and a K3, or it's going to be a 7 torus. So we really want these irreducible G2 manifolds. And you can determine this by the topology, because if your manifold is compact, you can show that if your G2 structure is torsion-free, then it'll be irreducible if and only if the fundamental group is finite. So if you know the topology of the manifold you're working on, you don't have to worry about this technicality. You just want to solve nabla equals 0 or t equals 0, and then it'll be irreducible. Okay, there are lots of examples of complete but non-compact torsion-free G2 manifolds, and most of these are explicit cohomogeneity 1 constructions. So you assume that there's some group acting on your manifold with orbits of codimension 1, and then you write down an ansatz for your G2 structure, your 3-form, in terms of the symmetry. So basically, all that really matters is this, everything depends on this one parameter which describes the space of orbits. And then you write down the torsion-free condition, and you get a fully nonlinear system of ODEs, but sometimes you get lucky and you could actually solve it explicitly. But one can show that if you want irreducible and compact, they cannot have any continuous symmetry. Basically, because they're Ricci flat, if you had a killing field, a non-zero killing field, it would be the holonomy would reduce because the killing field would be parallel. Okay, so you have to work a lot harder to find compact, irreducible G2 manifolds. You cannot reduce it to ODEs. And there's two main approaches: the elliptic approach and the parabolic approach. So from now on, for the rest of the talk, I'm going to always assume the manifold is compact. Some of what I say doesn't need it. In fact, maybe half of what I say doesn't need it. But I don't want to be careful and say, here I need to assume compact and here I don't. So we'll just take it to be compact for the rest of the talk. Okay, so the first sort of fundamental existence result about torsion-free compact G2 manifolds was due to Joyce in the mid-90s. And essentially all the known constructions, there's hundreds of thousands, or maybe now it's in the millions of examples of compact irreducible torsion-free G2 manifolds. And they all basically come from this existence theorem. Basically, you start by building something which almost solves the equation you want, and you use Joyce's analytic result to prove that you can perturb it to a nearby honest solution, right? So his theorem goes like this. Suppose you have again, we're on a compact manifold. Suppose you have a positive 3-form which is closed. Remember, we want to have closed and co-closed. And suppose phi is almost co-closed in some precise sense, which I'm not going to state. Some C0, L2, and L14-1 estimates on the norms of the torsion. Sorry, this is not quite right. I should say L14, because anyway, let me not get it wrong. But there's some precise estimates he writes down in his theorem. And if that's true, if it's sufficiently close to being co-closed in some precise sense, then there is a nearby torsion-free one in the same cohomology class. And moreover, the nearby one in some C0 sense, and modulo diffeomorphisms isotopic to the identity, this is the unique torsion-free G2 structure in this class that's sufficiently close to the one you started with. Okay, so here's the idea for how he does it. He wants to stay in the same cohomology class. So the new one will be the old one plus D of a 2-form. And then the condition of being torsion-free plus this gauge fixing, because if you pull back torsion-free G2 structure by diffeomorphism, you're going to get another torsion-free G2 structure. So he does a gauge fixing condition, and then that system of equations becomes this nonlinear PDE, whereas Laplace eta is some quadratic thing in d eta. And you can solve this. You can show that there exists a unique solution for eta sufficiently small, or for d eta sufficiently small, assuming these estimates on the initial torsion. Okay, I want to say a little bit more about how you should think about this. So Hitchin had a variational approach to torsion free.
Yeah.
Yeah.
The did you say before that if you're looking for the full holonomy, not for the whole ring,
Yeah,
you want G2 holonomy,
Yeah.
then you can't have any killing field. It's not, you can't have.
you can't have any,
Any. Right?
Yeah.
So all of these have absolutely no killing.
that's right.
And how does one produce hundreds of thousands of examples?
Basically, you can compute B2 and B3 for these manifolds.
But
And
so are there 100,000 people who are doing this kind of thing?
no, there's three or four main constructions,
Okay.
and from those ideas, they produce
Okay.
lots. The one, I mean, until about 15 years ago, there was Joyce's construction, which is a resolution of these torus orbifolds, and Kovalev's twisted connect sum construction, and those together probably produced several hundreds, maybe about 1,000, and then
So the computer doesn't, or there are-
yeah, I mean, they do it. I guess they do it on a computer. Yeah, and Corti, Haskins, Nordstrom, and Pacini improved Kovalev's connect sum construction, and they got hundreds of thousands or millions. Yeah. But everyone expects these to all be sort of special, like it's a very small corner of the landscape of G2 manifolds that we're finding, because they're all sort of built by things that are about to break or go bad, right? Something that's about to become singular or detach into two pieces, so they should be near the edge of the moduli space.
Right.
Okay. So very quickly, what Hitchin did is he says, suppose you start with a closed three form, just like Joyce, and you look in that cohomology class, you look at all the other non-degenerate three forms in that cohomology class. This is an open set of closed G2 structures, and you looked at this functional. So given a positive three form in this cohomology class, it induces a metric and an orientation, so we get a volume form, and let's look at the volume of the manifold with respect to phi tilde. And he showed that the critical points of this are torsion-free G2 structures, and they're always local maxima. Yeah.
Actually, going on that question, do you expect there to be infinite families of these things, or?
They always come in families. Whenever you have one, there's the moduli space is a finite dimensional smooth manifold. Whether there should be sort of infinitely many distinct topological types, I don't know. I mean, that's just, what about Calabi-Yau threefolds, right? Probably not. Okay. So Hitchin basically showed us that the torsion-free ones, if you stay in a fixed cohomology class, they're local maxima of this volume functional. And we don't know if you can have more than one critical point for this functional, right? So first of all, there may be no critical points because that cohomology class might have no torsion-free G2 structures in it. But even if it does, the only thing we know from Joyce's theorem is that it's locally unique. There's not another torsion-free one in that cohomology class sufficiently close to it. But far away, there may be more. That's what I'm saying here. Okay, so now we can finally get to some flows, and I'm probably a bit behind. So recall, this is what we want to achieve, torsion-free, and that's equivalent to closed and co-closed. And that, because now we're restricting to compact manifolds, is equivalent to being Hodge harmonic. So motivated by Dominic's success in starting with a closed three form and then perturbing it to a nearby torsion-free one in the same cohomology class, Robert Bryant introduced the following geometric flow of G2 structures, which is now called the Laplacian flow. It should be called the Bryant flow or the Hitchin-Bryant flow. It's d phi dt is Laplace phi, with the initial condition being a closed G2 structure. So Robert and his former student Feng Xu proved the following theorem. If you start with a closed G2 structure, then this flow has short time existence and uniqueness, right? And it remains closed for all time.
What is Laplacian D? So what is
It's d star plus d star d. So it's not nabla star nabla.
okay?
It's the Hodge Laplacian.
Okay.
Yeah. I think I know what you might want to ask me, but maybe I won't predict it. Okay. So what does this theorem really say? Right? Why am I going to sort of pick on this? I'm not going to pick on it, but I just want to make sure we understand what it says and what it doesn't say. So what they actually showed is the following, right? Let's assume that our solution is of this form. This is forcing it from the very beginning to stay in the same cohomology class, right? So we're looking for a solution of this particular form. Then if you write down for phi t necessarily of this form, you write down what Laplace d of phi t is, it's this, right? And they prove that this flow has short time existence and uniqueness on the space of exact three forms, okay? The usual de Turk trick doesn't work here. But they were able to use a Nash-Moser implicit function theorem type argument. I don't want to spend too much time talking about that. You can ask me afterwards if you're interested. But what I want to emphasize is that, maybe I'm.
So you use the trick if you have a non-scripted parabolic equation.
Yes.
To gauge modified and make it strictly parabolic.
That's right, but
It is not strictly parabolic.
this is not strictly parabolic. It has
Yeah.
diffeomorphism invariance, but the usual Dirac trick doesn't quite work. Basically because,
But I'm a bit thick, so I thought. I don't know anything about the grammar. You can just write the symbol. You can just write it. So
Yeah.
Oh, it's DB star, not D star B. I see. So that's what.
Yeah.
That's what, is that the?
that's part of the issue. No, I mean, the issue is that they're forcing it to work in the space of exact three forms, right? They were working in this space, D of exact two forms, right? And this is not a Banach space, but if you look at D of like CK alpha two forms,
Yeah.
then it will be okay. So you could avoid the Nash-Moser implicit function theorem and use the usual Banach space implicit function theorem if you use polar spaces instead of smooth forms. They're not analysts. And so they made it harder than it needs to be, but even then, like the usual Dirac trick doesn't work exactly because you're sort of fixing this cohomology class to begin with. Okay. And in fact, this flow is the positive gradient flow of the Hitchin functional, right? Remember the critical points were local maxima, so you got to flow uphill, and you can show that in some precise sense this is a positive gradient flow. But I want to say, you'll often hear it said that Laplacian flow of G2 structures preserves the closed condition, but it's not really accurate to say that. What this flow that they proved has short-time existence was deliberately set up to flow within a cohomology class. Okay, so by construction, it's going to preserve the closed condition. And this is one of the reasons, though, as I said, why proving short-time existence is a bit non-standard. Usually, when you talk about flows and you say that some condition is preserved along the flow, what you usually do is you prove that the flow itself has general short-time existence without any initial assumptions. And then you show that if some certain condition holds at time zero, then it flows for all time for which the flow exists. And usually this is done using the maximum principle. So for example, positivity of scalar curvature under Ricci flow, or the Lagrangian condition under mean curvature flow in a Kähler-Einstein manifold, these are all things where that flow in general has short-time existence. And then if you assume some condition at time zero, that condition is preserved for all time because of some maximum principle argument.
But can't you just say, like, if you have any solution, just differentiate your equation, then you see that big close is preserved?
That's so you're saying if you know that there's a solution, you're saying d phi dt is Laplace phi.
Because D commutes with the Laplacian.
Yeah, so if you know there's a unique solution, yes. If you know there's a unique solution to d phi dt is Laplace phi, then it has to preserve closeness. But what I was going to say here is if you just look at this flow and you do not assume that you're flowing in the same cohomology class, we don't know if this flow has short-time existence in general. If it does, and if it has uniqueness, then definitely there's only one solution. So it is the solution to the Bryan-Shue flow because they both solve the same equation and there's only one, and therefore it would be preserved. So we don't have to do any more work to show that the closed condition is preserved by this flow if we know that it has unique solutions, right?
So uniqueness is the
Uniqueness is the problem.
So that's where
So
maximum principle is getting.
yeah, so I don't think anyone believes that, if you run this flow with an initial closed condition, that there might be more than one solution. I think everyone believes that it is unique, but I don't think this has been proved.
So the question is that PD logical?
Yes, that's the question.
And I think what you're saying is you can take Laplacian and then project onto the closed free form. That's the PD you're actually solving.
That's what they
The
did. That's right.
free form,
That's right.
whatever, and then you project onto that.
That's right.
And then you're saying that is well.
Yes, and this one is probably also well posed, but nobody has proved this as far as I know.
And this is not a compact manifold, so there's no boundary.
There's no boundary. Yeah. Good. All right. So let me tell you some things that are known about the Laplacian flow, because it is the most studied flow of G2 structures and a lot is known. Has some very nice properties. These results are due to Jason Lotte and Yang Wei. So they figured out that the blow up time, this is what happens, right? Either the curvature or the covariant derivative of the torsion will blow up at the singular time. They proved stability. If you start out sufficiently close to a G2 structure that's torsion-free, you'll have long-time existence and convergence to a torsion-free one, which is diffeomorphic to this. Using Joyce's existence theorem, if you know that your initial G2 structure is closed and almost co-closed, then you know because of Joyce's theorem, you know there's a torsion-free one nearby, so the stability will give you long-time existence and convergence. There should be a way to prove this independently. if the initial torsion, if it's closed and the initial torsion is small enough, you should have long time existence and convergence. Should be a way to prove that without appealing to Joyce's existence theorem. This hasn't been done yet. They prove the solution is, yeah.
Maybe, and this, you seem to be saying there's some sort of convexity. So if you know that there is a solution, then this flows and you will flow to that solution.
Modular diffeomorphisms. That's right. That's right.
Okay.
You might not flow exactly to that, but it'll be in the diffeomorphism orbit of that solution.
That seems to say something about the stability of the solution.
That is it's a kind of
Also
stability.
not stable. It's not just there's some sort of stability there.
It's a maximizer of this volume.
Yeah, that's right. That's right. That's right. Exactly. Because that functional is what's called, it's a Morse-Mach functional. The critical points are non-degenerate. Okay, and let's, some people have studied the dimensionally reduced case of Laplacian flow. Let me talk about a couple of other flows because I want to get to my paper, which I haven't gotten to yet. So you can take the 4 form, and the 4 form can also be taken to be the fundamental object that sort of determines everything. The only issue there is that the 3 form actually picks out a preferred orientation, preferred as long as you choose a sort of convention that everyone would agree on, which not everyone does. But the 4 form doesn't single out an orientation, and that's because the group that preserves the 4 form is G2 times plus or minus 1. But if you just fix an orientation to begin with, then the 4 form can also be taken to be the fundamental object, and it determines everything. The map from 4 forms to metrics is more complicated, but we're not going to need it here. So we want to achieve torsion free. That's the same as phi being closed and co-closed, but of course that's the same as psi being closed and co-closed, or Laplacian of psi equals 0. So you can ask for this, what we now call the co-flow, which is flowing the 4 form by a Hodge Laplacian of the 4 form and starting with the 4 form being closed. So I introduced this with 2 co-authors a long time ago, but we didn't talk anything about short-time existence. We were just looking at solitons for this flow. And if you look at the approach of Brian and Zhu for short-time existence, even the sort of harder thing they had to do, that's not like Ricci flow where they had to use Nash-Moser and all that, it doesn't work. And it's kind of mysterious a bit why it doesn't work. I'll say a little bit in a minute. But Sergei Grigorian modified this flow by adding this strange term to the right. And then this does have short-time existence and uniqueness. And the way that Bryant and Zhu proved short-time existence will work here in this sense, right? You're saying I want to stay in the same cohomology class, and I want to flow by this, and this will preserve closedness of the 4 form. But now, even though torsion-free ones are fixed points, there may be other fixed points of this flow that are not torsion-free. So something strange is happening here. And it's probably related. It seems to be related to the question of proving a 4 form version of Joyce's existence theorem. So if you start with a G2 structure, which is co-closed, that means the 4 form is closed, and sufficiently close to being closed, can we always perturb it or deform it in that cohomology class of the 4 form to get a torsion-free one? It looks like it's a little bit different. And I don't want to talk about this too much, but I'm trying to do this with Shubham Dwivedi, and I think that the reason this is a little more difficult is directly related to why this flow doesn't behave as well as the Hodge Laplacian flow for the 3 form.
Let's see.
It's a constant, arbitrary constant. Yeah.
That's supposed to be a 3 forms.
Well, sorry. This C minus trace T is multiplying the whole star. Yeah, sorry about that. Let me tell you about one more flow, and then we'll get to the general stuff. So remember I said that the 3 form determines a metric, but this map is not injective. So there's lots of 3 forms that give you the same metric. And if you give a fixed metric and you look at all the 3 forms which give you that metric, it turns out that at each point you get an RP7 worth. So there's an RP7 bundle of G2 structures inducing the same metric. So another question you can ask, remember this sort of philosophy of what's the best geometric object, instead of asking to get a torsion-free G2 structure, if we fix the metric and we say what's the best G2 structure giving a particular metric, we might want to minimize the torsion among all G2 structures inducing the same metric. So you look at this functional, the sort of L2 norm of the torsion, and you restrict it to the set of G2 structures giving a fixed metric, and you look at the negative gradient flow of that, and you get this flow. This is called the isometric flow or the div T flow. It was Sergey who first came up with this flow. So this, remember, T was a 2 tensor, the divergence is a vector field or equivalently a 1 form, and we hook it with a 4 form to get a 3 form. This one has short-time existence and uniqueness, and in fact, this is really nice. It's strictly parabolic. You don't have to do any determined trick. And the reason this happens is because the metric is fixed, so it's not diffeomorphism invariant.
This is over a finite dimensional space.
What do you mean finite dimensional space?
I think you said that the metrics that give.
Yeah, it's a finite. That's right. That's right. That's right. And so there was a lot of analytic results proved about this flow by Sergey and by myself and my co-authors in 2018. You can read it if you want, but I'm kind of running a bit behind time. But basically, the moral here is that you can do a lot more very easily with not very easily, with less difficulty for this flow because it's an easier flow. And the drawback of this flow is that it's not going to take you to torsion free, right? Because if you are torsion free, you're Ricci flat. And because the metric is never changing, you're not going to be able to construct torsion free unless you're already starting with a Ricci flat metric, which is unreasonable. Nevertheless, it is picking out sort of preferred representatives of G2 structures in a given metric class. And it is going to show up by the end of this talk again. That's why I wanted to, not just to plug our other paper, but to show you this in advance because it'll show up again.
The structure of the singular set isn't like.
We know that it's the Hausdorff codimension is at least 2. I can't remember exactly now. Let me look it up. But we know how. What's that?
Is it like calibrated? Right?
No, that we don't know. That we don't know, and I don't know what we would expect. Yeah. Okay. So, okay, I think we're okay on time. So I told you about the Laplacian flow, the coflow, the modified coflow, the isometric flow. Like why? It seems like a big zoo of flows. Why should we look for more? So what I would say is it's not clear yet that the Laplacian flow is the best flow to evolve towards torsion-free. It's the best in the sense it's had the most success so far, and it is sort of modeled on Joyce's elliptic result. So there's a reason to consider it. But I'll give you a couple of reasons why I think we should keep looking, maybe. One is that the proof of short-time existence, to me at least, is unsatisfying, given that we build in preservation of closeness from the outset. And it's also not clear in the setting of G2 geometry if the right thing to do is to start closed and stay in that cohomology class, right? We don't even know if there's a unique torsion-free in a given cohomology class, even if one exists, right? We don't have global uniqueness. And you should compare this, of course, with the classical case of Taylor and Calabi-Yau geometry. Yau's theorem says if C1 is 0, then if you start with a Taylor form, then you can find a unique Ricci flat Taylor form in that cohomology class, and it's the only one in that whole class. Okay, and there's a parabolic version of that, which is Taylor-Ricci flow. And one reason why this is sort of more tractable, it's very, very difficult, but the feature it has, which is not present in G2 geometry, is you have this DD bar lemma. So you can reduce things from first order systems to second order single equation, right? It's fully nonlinear modular pair equation is very hard, but it's a second order PDE instead of a system of first order PDEs. And one of the ways to think about why this happens is because in Taylor geometry, essentially the complex or the symplectic or the Riemannian geometry, they're all kind of independent. Any two are sort of independent from each other. They have these mild compatibility conditions, but any two of them will determine the third. But in G2 geometry, there's no decoupling like this. You can't say G2 geometry is the intersection of Riemannian geometry and something like complex or symplectic geometry. The 3 form, there is something that plays the role of the J of the complex structure, and the 3 form plays the role of the symplectic structure. But the 3 form determines the cross product and determines the metric. Okay. So what would be a good flow of G2 structures? So the first thing we can ask for, of course, if it doesn't have short-time existence and uniqueness, then game over. We're wasting our time. Okay. And just because I love the Ricci flow so much, I would like to find a flow where you can use a Duterte type trick to get short-time existence and uniqueness, right? To show that it's equivalent to a strictly parabolic heat-like flow. So because it's going to be a heat-like flow, the right-hand side is going to be some second-order, quasi-linear, second-order differential invariant of a G2 structure. Okay, so the first thing we need to do is, and of course, the right-hand side is a 3-form. So we first need to figure out what all the independent second-order differential invariants of a G2 structure are, which are 3 forms. There are lots of second-order differential invariants of a G2 structure. They're not all 3 forms, but there's more than there's several that are 3 forms. So I need to take a short digression here on the representation theory of G2. Basically, we need to figure out how to decompose various representations into irreducible G2 representations. So I'm just going to tell you some facts, just so you can understand the sort of statements that follow. So if you look at the space of symmetric 2 tensors, this breaks up in exactly the same way as it does on any Riemannian manifold. There's the multiples of the metric. These are the pure trace. And then there's the trace-free, the ones that are orthogonal, pointwise to the metric. It doesn't break up any further. The space of 2 forms and the space of 3 forms both break up when you have a G2 structure. And this omega 3,1 is just functions times phi times your G2 structure. So it's isomorphic to this guy, space of functions. All these 2 guys that have a 7 as a subscript are isomorphic to 1 forms or vector fields. And this guy here is isomorphic to traceless symmetric 2 tensors. Okay. The 14 one, I'm not going to talk about it too much. It's not so important for us in this talk. But the moral here is that if you want your right-hand side of your flow, it has to be a 3-form. You're flowing your 3-form. d phi dt is going to be some p of phi, which is a 3-form. There are 3 different kinds of things they can be. They can be basically functions, vector fields, or traceless symmetric 2 tensors. And explicitly, the way you can package this information together is if you have a symmetric 2 tensor H and a vector field X, I'm always going to identify vector fields in 1 forms. Then what you do is you can contract H with phi on a pair of indices. It's no longer skew symmetric, so you skew symmetrize it. And you can contract your vector field X with the 4-form, and that is a 3-form. Okay? This is every 3-form. If you fix a G2 structure, every 3-form can be written in this way for a unique H and X. And so we want to find all the second-order differential invariants of G2 structures, which are vector fields or symmetric 2 tensors. It just makes sense to package, instead of splitting these into 2 pieces, we're going to package them together. Okay? So these are the ones that can be 3 forms.
Sorry.
Yep.
I want to understand the boxed equation.
Yep.
So, did gamma determine hx and phi, or?
No, phi is fixed from the beginning.
Okay.
Now, once you fix phi, any 3-form gamma determines H and X.
Any other 3-form, or just it's
Any 3-form, doesn't have to be positive. The space of all 3 forms.
Okay.
You should think of this as kind of like the decomposition into forms of type PQ in a complex manifold, but the sort of pieces are a little bit weirder. Right? Okay. Good. So, let's look at this decomposition here. First of all, remember that I said the torsion was a 2 tensor, so it has a symmetric part and a skew part. The symmetric part breaks up into the trace and the trace free, and the skew part is a 2-form, so it breaks up into the 2,7 and the 2,14. So the pure trace part is just, because it's a 7-dimensional manifold, it's 1/7 times the trace of T times G. This guy I said is isomorphic to a vector field, and explicitly that means there's some vector field, I'll call it T arrow, such that when you hook it into the 3-form phi, you get this omega 2,7 part of T7. And this T27 is some symmetric traceless 2 tensor, and we don't care so much about this. Okay, so let me remind you something that many of you know, that if you just have any Riemannian metric, you can decompose the curvature into scalar curvature, trace-free Ricci curvature, and Weil curvature. Okay, the Ricci curvature, the scalar and the trace-free Ricci, don't decompose further in the presence of a G2 structure, but when you have a G2 structure, the Weil curvature breaks up into 3 pieces. And these are the pointwise dimensions of these tensors. They're sections of bundles of this rank. This was due to Clayton and Ivanhoe. So the important thing to take from this is that this guy, part of the Weil curvature, is a traceless symmetric 2 tensor. There's only one irreducible G2 representation of dimension 27, and it's the symmetric traceless 2 tensors. So you can make scalar curvature and traceless Ricci curvature into three forms. And you can also make 1/3 of the Weil curvature into a three form. So that's all you get from the curvature, right? One of the second order differential invariants of any Riemannian manifold, or the only one, is the Riemann curvature. And it breaks up into 5 pieces here, and 3 of these pieces can be used as three forms to flow the three form. I want to talk about a few more invariants that come from the torsion. It's going to be convenient to introduce this symmetric 2 tensor. If I take the curvature tensor and I contract with phi on the first 2 indices and with phi on the last 2 indices, this is obviously symmetric in I and J. And you can show that this W27, which was on the previous slide, I didn't show you the formulas for that, they're horrendous, but it's basically expressible in terms of F, R, and traceless Ricci. And the advantage of that is this is a lot easier to deal with than W27. So if we just care about the independent second order invariants that are three forms, which come from the curvature, it also doesn't make sense to work with traceless Ricci. It's unnecessarily complicated because RG and Ricci span the same space as RG and traceless Ricci. So we got scalar times metric, Ricci, and this guy F, and any second order differential invariant coming from a G2 structure, which can be made into a three form, is some linear combination of these. Okay, but you can get more from the covariant derivative of the torsion. And here I'm not going to list them all because there's a whole bunch of them. But for example, you can take the divergence of the torsion, that's a vector field. You can take the divergence of the transpose of the torsion, which just means take the divergence on the last index instead of on the first. You can take the gradient of the trace of T. You can take nabla T and contract it with a 4 form on 3 indices. That's a vector field. You can contract nabla T with phi on 2 pairs of indices in 3 different ways, and then take the symmetrization of that. These are symmetric 2 tensors, and these are vector fields. So all of these could be second order differential invariants. So they're not all independent. There's a relation which I proved a long time ago called the G2 Bianchi identity. For any G2 structure, there's a relationship between the torsion and the curvature. Basically says that some skew symmetrization of nabla T is essentially T squared plus R. And when I discovered this a long time ago, it was very mysterious to me, but now I know very, very simple ways of proving it, and other people have also found simpler proofs. It's not that mysterious anymore. But basically, this tells you that nabla T and R are not independent. They're related by this Bianchi identity, G2 Bianchi identity. So you can take this guy, if you look at it, it's skew in I and J, and then there's no symmetry with L. So it lives in wedge 2 of T star M tensor T star M. And you can decompose that space into irreducible G2 representations. So you can show that this identity decomposes into independent relations between curvature and nabla T. And it turns out to be 7 independent pieces. One of them relates the 64-dimensional part of the Weil curvature with a 64-dimensional part of nabla T. We don't need that one. The other ones involve 27s and 1s and 7s. So when you decompose this and you see what the relations are, then you prove that there's only 6 independent, linearly independent second-order differential invariants of a G2 structure. It's the 3 that I showed you before coming from curvature, and you just get 3 more from nabla T. You get this guy. Remember, there was a piece of the torsion which was a vector field. You can take the Lie derivative in the direction of that vector field of G. It looks first order, but remember, this differentiates the vector field down there, so it's second order. And you can take this div T and div T transpose. If you go back to the previous slide, all these guys down here, these 2, turn out to be equal to these up to lower order terms. So when I say independent, I mean up to lower order terms. And these as well, all of these turn out to be equal to these 4 up to lower order terms. Okay, so the punchline is, if you want your flow to be second order quasi-linear, then any flow of G2 structures, it has to be d phi dt is some linear combination of these 6 plus lower order terms. And because we only care in this talk about the short time existence, which is only going to be affected by the symbol, we're going to ignore the lower order terms until the very end. Okay. So let me state the main theorem. So remember, we're going to have d phi dt as a 3 form, and that 3 form is determined, it determines uniquely a symmetric 2 tensor and a vector field. So we want to choose H, we're going to choose our H to be a linear combination of these four, and our X to be a linear combination of these two. And then there's lower order terms, which we're ignoring. And then ask ourselves, for which of these flows do we know we can prove nice short time existence using a deterk type trick? And we're not going to assume anything about the initial torsion. So we're not going to assume it starts closed or conclosed. And so for the purposes of this this talk, I'm going to simplify things a little bit. I'm going to take the coefficient of Ricci to be -1. I'll say why in a second, and I'll take I'll omit the RG term. It's a little messier.
But I'm not understanding the first equation, 1B.
Here?
Right? That doesn't look like a PD at all. I don't know what you.
No, H and X involve second derivatives of phi.
Oh, I see.
Yeah.
It's
Right.
just to make it the right.
Yeah.
To make it the right. type of-
So H is going to be some combination of these, and X is going to be some combination of these.
I see. Okay.
Okay, so I'm omitting the RG term, and I'm taking the coefficient of Ricci to be -1. If these two guys weren't here, if you're just flowing with H as minus Ricci, then the metric flows exactly by Ricci flow, right? So if A and lambda are 0, then this will induce Ricci flow plus lower order terms on the metric. And this X doesn't affect the metric variation at all, right? So if you're flowing phi by this, then the flow of the metric is 2H. That's why we want a -1 here for convenience, right? So we know we're getting our metric to flow in a nice way. It'll be Ricci flow plus possibly corrections to Ricci flow. Okay, so here's the theorem. Okay, let me go back. So we have A and lambda here, and we have B1 and B2 here. So there's some horrendous bunch of inequalities. If these inequalities are satisfied, then this flow has short-time existence and uniqueness, and you can really do a slightly modified deterp trick. You don't have to do any of the hard work that Bryant and Xu did for the Laplacian flow. And there's some special cases that are included in this. If you take A to be -1/2, lambda is 0, B1 is 1, B2 is 0, you get the negative gradient flow of the L2 norm of the torsion. And this was originally studied using spinorial methods by Frederick Witt and Hartmut Weiss. And they had proved short-time existence and uniqueness for this, the negative gradient flow of this. So that's now a special case of this result. And if you take, this is the one I like more, if you take A and lambda and B2 to be 0, so we just take minus Ricci here, and B1 to just be 1, then what you're getting is that the metric is flowing by exactly Ricci flow plus lower order terms. And the free form is essentially flowing by a combination of Ricci flow with the isometric flow that came up half an hour ago, right? D phi dt is div t hook psi. That's what's coming here. So if you, but the important thing is if B1 was 0, if you just took Ricci flow on the nose, then these inequalities are not going to be, this one's not going to be satisfied, right? So this is not an if and only if. These are sufficient, but they may not be necessary, right? But Ricci flow on the nose doesn't immediately seem to have a good deterk type trip for the G2 structures. But if you couple it with this isometric flow, then it does play well. It does behave well. It has short-time existence and uniqueness. Okay, so let me just say a little bit about the idea. So we compute the principal symbols of all these second-order differential invariants, and we show that when those inequalities are satisfied, the failure to be strictly parabolic is exactly due to diffeomorphism invariance and nothing else. And to do this, we have to analyze the usual Bianchi operator from Ricci flow, and then a G2 specific operator. This is the cross product. So there's a cross product on a manifold G2 structures, which is a way of taking two vectors and giving you another vector, which is skew symmetric, has a lot of the same properties of the cross product in R3, but it's a little bit different. So you need to think about this operator as well. And then we do a slight variation of Deturk's trick. So, you know, the usual thing is to modify the right-hand side of the flow by adding a term involving a Lie derivative for some fixed vector field, or for some prescribed vector field. And if you ignore this last term here, this is exactly the vector field you use to do Deturk's trick in the Ricci flow. But we have to add, if A is not 0, we have to add this part where T arrow is the vector field part of the torsion. So when you do this, you get a strictly parabolic flow that's equivalent to the original flow. And then there's one extra step to prove the uniqueness, because the way that uniqueness is proved for the Ricci flow using the Turk trick is by showing that these diffeomorphisms satisfy some harmonic map heat flow and using uniqueness of the harmonic map heat flow. So because you don't get that exactly because of this term, you have to do an extra step, but this is not difficult. Okay, I think this is my last slide. I think I'm just coming out of time. Of course, a lot still has to be done. Short-term existence and uniqueness only depends, of course, on second-order terms. Other more interesting properties of the flow, like characterizing what exactly are the fixed points, they're very, very sensitive to what those lower-order terms are. So, for example, if we take Ricci flow coupled with isometric flow, this will have short-time existence and uniqueness, no matter what the lower-order terms are. But can we choose these lower-order terms so that the fixed points are exactly the torsion-free ones, right? Certainly, the torsion-free would be fixed, because all these lower-order terms are essentially t squared, torsion squared. So if the torsion-free, everything goes. But what we would like to say is it's not true that if you have a G2 structure which is Ricci flat, then it has to be torsion-free, because there are other G2 structures giving you the same metric. So they'll all be Ricci flat metrics. It'll be the same metric, but the other ones don't have to be torsion-free. But you could ask a condition, which is Ricci flat plus more, which would force it to be torsion-free. So for example, it's the theorem of Bryant and Clayton and Ivanov that if it's compact, closed G2 structure, the free form is closed, and it's Einstein, then in fact it's torsion-free and Ricci flat. Right? So something like that, where you're imposing some second order condition and compactness, and you hope that some integration by parts argument will force it to be torsion-free. Another good thing to impose on the flow is whatever our flow is, we want to pick the second order term, the lower order terms, to potentially force the pointwise norm squared of the torsion to flow by a heat equation with good signs, right? So we can use maximum principle and get some kind of monotonicity. And then, of course, all the usual questions that come, right? This is just step one, right? I think that's okay. That's all I want to say. Thanks.